Welcome to the Azhdar data card video. Everything we have covered in this series so far has been in the air domain. Missiles, drones, kamikaze weapons, platforms that fly. Today we go underwater. And when you go underwater, the defender's dilemma gets worse. Much worse. Because underwater there is no AGR-20 equivalent. There is no cheap intercept solution. And the platform we are covering today may already be operating in one of the most strategically critical bodies of water on the planet right now. The Azhdar. In Persian, the word means dragon. It is Iran's unmanned underwater vehicle, a UUV, and it is the subsurface expression of the same asymmetric warfare philosophy that gave us the Shahed 136 in the air domain. Same country. Same strategic logic. Completely different operating environment. And a defender's problem that is significantly harder to solve. Let me start with what we know, and I want to be transparent about sourcing on this platform, because several of the detailed specifications come from analytical assessments and intelligence community evaluations rather than confirmed public disclosures. Where that is the case, I will say so. The overall platform concept and its operational implications are well established. Some of the specific performance figures carry uncertainty. The Azhdar originated as a repurposed Igavasi swimmer delivery vehicle, essentially a human torpedo design that Iranian engineers converted to autonomous unmanned operation. The conversion required sensor integration, a commercial off-the-shelf navigation system, communications capability, and a central processor. According to analytical assessments, the processor used is something as simple as a Raspberry Pi class device. The engineering elegance here is the same as the Shahed: take something that already exists, remove the human from the design constraint set, add autonomy, and produce a weapon at a fraction of what a purpose-built system would cost. The hull diameter is 533 millimeters. That is not an accident. 533 millimeters is the standard diameter of a heavyweight torpedo tube. The Azhdar is torpedo tube compatible. Every Iranian submarine, Ghadar-class midget submarines, Kilo-class conventional submarines, becomes an Azhdar launch platform without any modification. The forward diving planes and rear stabilizers fold and recess into the hull for launch, then spring deploy after ejection. The launch event is indistinguishable from a torpedo launch until the weapon fails to arrive at torpedo speed. Propulsion is lithium-ion electric battery, 50 volts, driving an electric motor. This is the detail that keeps naval engineers awake. An electric motor at low speed in shallow water produces an acoustic signature that is essentially indistinguishable from background noise. The Persian Gulf averages 50 meters depth. Shallow water sonar performance is severely degraded by thermal layers, shipping noise, biologics, and bottom reverberation. You are trying to find a quiet electric motor in a very noisy shallow sea. The detection problem is genuinely hard. Estimated speed is 18 to 25 knots in active pursuit mode. Patrol and loiter speed is much lower, approximately 3 to 6 knots, which maximizes endurance. Assessed endurance in active mode is approximately 20 hours with a range of 127 kilometers. In patrol and loiter mode, endurance extends to 24 to 96 hours depending on speed profile. Some assessments put standby endurance at up to 4 days. Operating depth is up to 200 meters, more than sufficient for the Persian Gulf's maximum depth of approximately 90 meters. The warhead and payload bay can accommodate up to 480 kilograms, a seabed mine, a direct attack warhead, or other mission payloads. The fusing options include time delay, GPS position trigger, magnetic influence from a ship's hull signature, acoustic trigger, and contact fuse. The operator sets the mission parameters before launch and the vehicle executes autonomously. There is no operator in the loop after deployment. There is no communications link to jam. There is no data link to intercept. It goes where it is told to go and it detonates when and how it is told to detonate. This is the mobile mine concept, and it is the genuinely new capability that makes the Azhdar strategically significant beyond its individual lethality. A traditional mine sits on the bottom and waits. Minesweeping clears lanes. The mine stays in the lane you swept. A mobile mine moves. If you sweep a lane, the mobile mine repositions. Conventional minesweeping is defeated entirely by mobility. The Azhdar is not just a mine. It is a mine that can follow a ship. Let's take a closer look at the countermeasures. Countermeasure vulnerability profile. RF jamming, low. Primarily autonomous INS navigation. Minimal RF exposure during operation. No active communications linked to jam. GPS spoofing, low to moderate. Pre-programmed INS navigation is primary. GPS used for initial positioning where available but not required for terminal approach. EMI and EMC attack, low to moderate. Military electronics with some hardening. Hybrid drive electronics present some vulnerability surface but not consumer-grade exposure. Microwave attack, low to moderate. Limited external antenna exposure during submerged operation. Significantly less vulnerable than aerial platforms. Acoustic detection, very low. Electric propulsion near silent. Shallow Persian Gulf water severely degrades sonar performance. Magnetic detection, moderate. Vehicle has magnetic signature but MAD is operationally challenging in shallow cluttered water. Kinetic intercept, very low. No practical intercept solution currently fielded for slow-moving subsurface autonomous vehicle in contested shallow water. Mine countermeasures, low effectiveness. Vehicle mobility defeats conventional minesweeping entirely. Cyber attack, low. Pre-programmed fire and forget architecture. No active communications link during operation. Counter-UUV systems, emerging. U.S. Task Force 59 deploying detection capability. No proven low-cost intercept solution yet fielded. Overall vulnerability rating, low. Operating environment defeats defender sensors before engagement begins. Now the operational history, and I need to flag the sourcing carefully here. The May 12, 2019 Fujairah tanker attacks remain officially attributed to an anonymous state actor using limpet mines. Analytical assessments by multiple intelligence-adjacent organizations concluded that Azhdar UUVs deployed from Ghadir-class submarines were responsible. That assessment has not been officially confirmed, but it has not been officially refuted either. For tankers attacked while anchored off the port of Fujairah, the attack profile, precision targeting of ships at anchor with no visible surface activity, is consistent with autonomous UUV deployment and inconsistent with diver-placed limpet mines at the distances involved. In February 2024, the U.S. Coast Guard seized UUV and USV components from an Iranian dhow, confirming Iran is actively supplying underwater drone technology to Houthi proxy forces in Yemen. In the same month, U.S. Central Command confirmed it struck Houthi UUVs, the first confirmed Houthi employment of a UUV since attacks began in October 2023. The Strait of Hormuz situation right now, and this is current as of today, has U.S. Navy officials describing the strait as an Iranian kill box in part because of the underwater drone threat. Over 300 ships are currently stranded in the Gulf. The cost of escorting a single tanker through the strait has been assessed to exceed the value of the cargo it is carrying. Now let me give you my engineering read on the cost exchange argument, because this is where the subsurface domain diverges most sharply from everything else we have covered in this series. In the air domain, we have a partial answer to the cost exchange problem. The AGR-20 Falco at $22,000 to $25,000 per round inverts the ratio against Shahid-class threats. It is not a complete solution, but it is a credible one. Underwater, there is no such answer. The primary kinetic counter to an Azhdar-class threat is the Mark 48 torpedo at approximately $1.5 million per shot. Against a vehicle that costs tens of thousands of dollars assembled from commercial components and repurposed military hardware. The cost exchange ratio is catastrophically unfavorable for the defender, potentially 50 to 100 to 1 in the attacker's favor, and there is no fielded cheap intercept solution on the horizon. The subsurface domain has the same cost exchange asymmetry problem as the air domain had before the AGR-20. The difference is that nobody has solved the subsurface version yet. Task Force 59 is working on detection. Detection is only the first part of the problem. What you do after you detect a slow-moving autonomous underwater vehicle in 50 meters of water in a contested strait is a question that current naval doctrine does not have a clean answer to. That gap, between the threat that exists and the solution that does not, is one of the most important unresolved problems in naval warfare today. And it is operating right now in the Strait of Hormuz. The full Azhdar data card is available at the link in the description. Download it, keep it, and we will see you on the next one.